Welcome, everyone. I'm Gabriele Granello, Wikihouse Engineering Lead. And in this video today, I would like to talk to you about OSB. Before talking about that, however, I would like to start actually talking about plywood. And that's because you most likely have seen a lot of Wikihouse testing done on plywood. The reason for that is because plywood is an excellent material, and it's most likely to be the strongest panel that you find in the market. We have carried out extensive testing with plywood, and if you wanna see more, I'm gonna link a video here in the description about some testing that we carried out on structural beams made of plywood. Despite plywood being an excellent material, it has some drawbacks, and specifically is not a local product to the UK. It is in fact manufactured outside, overseas, most of it in the northern countries like Sweden, and for is important in the UK. So we were wondering with the Wikihouse team if we could bring the carbon footprint cost of Wikihouse and the cost itself of Wikihouse even lower by using a product like OSB, which has the great advantage that is manufactured locally. OSB stands for Oriented Strand Board, and essentially is a timber panel which is fabricated by using timber strands, which are compressed and glued together to form a panel. For Wikihouse specifically, we normally use 18 millimeters thick panels, the dimension of 2.4 meters times 1.2 meters, roughly. So this idea of using OSB is not new to us. Actually, we started already in 2021 in testing some OSB in a partnership with the University of Edinburgh. Specifically, we were testing the material itself to understand its mechanical properties, and we'll show you some information about that. But it's only until recently that we were able to test some Wikihouse elements in a full-scale testing. And I'm going to give you more details of this latest experiment that we carried out in a partnership with the Imperial College in London, where we were able to test Wikihouse beams in what is called a 4-point bending test. The particular boards that we used were made of OSB 3, which is produced locally in the UK, in Scotland actually, by West Fraser. So the advantage of OSB is that because OSB is essentially locally sourced, the carbon footprint is lower, but also the transport costs are lower. It doesn't need to be imported, and for this reason is also cheaper. So what we really wanted to know with this test specifically is, can we build Wikihouse made of OSB? How does that perform, or how would it perform, and how would it perform with respect to plywood? And the first question in this direction is about beams and gravity load. So let's now jump into the numbers and see what happens if we swap the materials from a structural point of view. So first thing I would actually like to talk about is the material itself and that early testing that we did back in 2021, and where we test the mechanical properties of the material itself. Obviously, this is important because when we test a structural system, you want to know there's a lot going on essentially when you test a full structural system. So if you really want to understand the nuts and bolts of it, you need to start your testing by the simplest and basic component of the wall chain, which is the material itself. So the first question we were asking ourselves is, how does OSB compare to plywood in terms of mechanical properties? Now, for the engineers looking at this video, or for people experienced with construction, they may say this is not necessary to be done, because every product, and you will see in this report as well that is available on our website, every product that you use for construction comes with what is called a declaration of performance. So the manufacturer that you work with, the material you use, is well documented, and it comes with, for example, all the mechanical properties that you need to know. For example, the strength in compression, the strength in bending, the strength in shear, module of stiffness, module of elasticity, and obviously these are the values that normally are used for design. However, for probably some of you may not, some others might not, the values that you're given in the declaration of performance are characteristic values, most of them. And this characteristic has a probabilistic meaning. So imagine that we have our material, and then we have 100 specimens, and we break 100 of them. Obviously, the breaking capacity, the strength of the material is gonna, you're not gonna have 100 values equal to each other, but this value will follow distribution, which as structural engineering we normally assume is a normal distribution, which will have an average value and a standard deviation. Now, the characteristic value in probabilistic terms is the value corresponding to the 5% probability. Actually, it corresponds to the 95% probability to be overcome, which means it's a very, very low value on your probabilistic curve, and is as far from the average value for bigger values of standard deviation. So essentially, it doesn't represent the average value. Actually, it's a quite conservative value, which is good for design purposes because we want to be conservative as engineers. But when we do testing, when we try to understand how a structural system behave, we would like actually to work with the average value. Because if we develop some math, for example, to capture a specific failure mode, we want to really understand the accuracy of our math. And if our math is off because we are conservative since the beginning, then we are not really capturing the uncertainty coming from our model, but we are simply introducing uncertainty due to our conservatism. So when we do test, we normally carry out material testing to find the average properties. We have some experimental results. We develop some math to capture those. And then once we're happy with the math, that math used with the characteristic values normally is used for design. So what sort of tests we did? We carried out some compression tests, and you may find the results in this document. You're most welcome to download all the data. They are all public. And you can see all the details over there. But long story short, when we look at the average values in terms of compression strength, OSB is half, essentially, less than half that the compression strength of plywood. Here there are two values of plywood strength because plywood has a direction in which is stronger, which is the longest direction of the panel, and then a weaker direction, which is the shorter direction of the panel. That's because when the plies are actually glued together, they are glued in a specific direction itself. So you will always find two values when working with plywood, what we call parallel to the grain, parallel to the stronger direction, and perpendicular to the grain, which is the weakest direction. But you see here in terms of compression capacity, OSB is actually weaker than plywood. And in tension as well, you will see when we did a test, obviously our size sample was limited to, I think, between 5 and 7 samples, so results might not to be 100% accurate, but they still offer a good indication that even in this case, OSB was presented lower mechanical properties, lower strength than plywood in tension. What is interesting is that when we start looking at shear, which is a sort of failure mechanism where we try to shear off the material, so forming a weak plane, is where actually OSB is outperforming plywood. And that's because when the plies are glued together, they always have a sort of weaker plane. It doesn't matter which way you test it, but they always have a weaker plane forming to shear off the plies with each other. Whereas OSB, because you have all these strands that are glued in random locations, you don't see the formation of this particular shear plane. So when you measure the shear capacity with standard test and standard instruments, you find a shear capacity that is actually higher. So just to recap, essentially, OSB is weaker than plywood in compression and tension, but OSB is stronger than plywood on shear. This is what we found during our testing. So this is a material level, but how does that affect, how does this properties propagate into the structural system? So to do that, we need to actually look at the results on full-scale testing. So in this document, we present the experimental outcomes of the testing that we carried out the Imperial College Structural Laboratory. And just to give you an idea, the PDF is here linked to the comments. Data are also available. But essentially what we did is we tested in 4-point bending configuration OSB WikiHouse beams. We carried out a similar test on plywood, and you can find a link to that PDF in the comments. I will show you a snapshot later on of that document as well when comparing the results. But for the moment, let's focus on OSB. So we did test 9 specimens in total. Specifically, we test 3 different geometries. The first geometry is what we call Skylark 250, and we chose a L specimen in the sense of length of the span. The second family of specimen that we tested was the Skylark 200 series. So just to give you a reminder, 250 is the bigger version of the system, which is the depth of the cassette, and the space specifically to fill the insulation is equal to 250 millimeters. 200 series is where the depth of the section is smaller and you can fill in with 200 millimeter of insulation. And this specimen 2, this is specimen number 2. Family of specimens number 2. And then we tested also a new shrink version of the 200 series that in this PDF is called 150. That's because you can fit 150 millimeter of insulation, 150 millimeter depth of insulation, sorry. But please just be aware that what the 150 series is not a series per se. It's just a particular beams element that is 150 millimeters deep. Actually, it's a little bit deeper when you take into account the wall flange and so on. That is actually compatible with the 200 series. And essentially the idea behind that is that if you are building a single-story structure or a 2-story structure with a 200 series and you have a small span, you just need an element to act as a roof. Maybe the depth that you have in the 200 series is a little bit overkilling, so we wanted to have a slimmer element that is compatible with the 200 series just for the roof. So the 150 is not a serial per se, it's just an element that acts as a roof for the 200 series. And here are the structural drawings of it. I said that there are 3 familiar specimens because we tested 3 specimens for the first beam type, 3 specimens for the second beam type, and 3 specimens for the third beam type. And that's because we always want to have a little bit of statistical variability. For what I was saying before, when you break a timber beam, you're never going to get the same number. So you always try to have multiple specimens to calculate at least the average. There's some more details about the experimental setup in the PDF, but essentially what we are doing is we're using an hydraulic actuator, which is computer control that push down the beams, and all the load of the actuator is reparted on 2 single points, which are the 2 still elements over here in contact with the timber, and then is pushing down the beams. We are using a load cell to measure the amount of load going into the system, and we use string potentiometers to measure the deflection of the beam in 7 different points, 5 points along the beam profile, and 2 points between the beam and the column to measure any gap opening at the interface between beams and columns. And you might notice also we have some painting, white painting with black speckle pattern on the face of the beam, and I will comment more that on later, but we are essentially using a technique called digital image correlation to track the displacement and deformation of those speckles to have an idea essentially which points of the beam are subjected to highest force concentration. And I will maybe give you a little bit more details later on. So in terms of what we try to achieve with the experiment is obviously measuring the capacity of the beams. Normally that is quite important to that, and the stiffness of the beams. But it's also interesting to understand how they break and how they fail, because if we know how they break, then we can essentially develop some math and come up with a formula for the beam's capacity and the beam's deflection by using essentially theory and classical formulations that we normally use as structural engineers. And the interesting thing here is that most specimens reach the maximum capacity, or better, the failure was due because they formed this horizontal crack in the beam's web. Essentially what we believe is happening is when these tabs start working in compression, so pushing against each other, this tab is pushing against the vertical panel, then at a certain point the web actually can't take any more force, and it starts fracturing in tension here at the bottom. So the distance between the tab and the bottom is sort of the weakest link of the chain. You start feeling in tension over there, and once you open that part in tension, essentially it's like opening a zip, then the wall elements suddenly fail. And we can see this even in the force displacement curve. So if you plot the force at the actuator versus the displacement in the middle of the beam, you can have these curves where the red triangle essentially gives you the beam's maximum capacity. And so the top force, here they are expressed in kilonewton. And you can see essentially that once the beams reach the maximum capacity, the wall force drops quite suddenly. This is what we call a fragile failure mechanism, in the sense of once you reach the top capacity, the force suddenly drops essentially. And this is quite common on all timber material working in bending, because that's sort of classical bending failure. I will comment more a little bit on this, but this is essentially one of the main difference that we've seen with plywood. And let me show you what we actually found on plywood to make a comparison right away, and then we'll jump back on OSB. So just to give you an idea of difference of the behavior when using plywood, this is actually the report showing the test outcomes of the beams that we tested at the University of Edinburgh, which were made of plywood. And there's a link to this PDF in the comments, but essentially the test setup was exactly the same, the test protocol was the same. But what was very interesting in terms of failure mode is actually you see a different failure mode when using plywood. Specifically, you can observe the failure in compression of the tabs. So it's not like OSB where we have that main crack opening up, but we can actually observe the compression failure of the tab. And that is a completely different failure mode, and in fact is what we call a ductile failure mode. And if you see the force displacement loop, they tend to have a plateau or a little bit more a gentle degradation after reaching the maximum capacity. So this is one of the difference that we noted in terms of failure mode. But let's jump back to OSB now. So here we are back on our OSB specimens. The next step is essentially working out the capacity of the beams, which doesn't depend on the span. Obviously, we used, when we were testing, we test 3 different spans, but the capacity of the elements, the bending capacity of the elements is not, or it shouldn't be a function of the span. You can sort of retrieve the capacity of the beams by, in terms of bending capacity, divided by the 6 times the span. So you have the results in terms of bending moments, so you can compare the results essentially with each other. And when we start looking at the capacity of the beams, the OSB beams is interesting to see that essentially the 250 series is almost twice as strong as the 200 series in terms of capacity. So really shrinking down the section height has a tremendous effect in terms of capacity. And this is for 2 reasons. The first one, which is quite well understood by structural engineers, is that the capacity of the bending capacity of a rectangular timber beam, it goes with the powers of 2, so it's exponential with respect to your beam height. So essentially, if you're reducing your beam height by 2, your capacity drops by a factor of 4. So it goes with the scale, and that's because your section modulus is normally calculated with your depth of your beam to a power of 2. So the capacity is proportionate to that. But the second reason, which is even more interesting and probably more specific to WikiHouse, has to do with the distance between the tab and the bottom part of the beam. Now, this is a little bit more complicated and subtle, and but I think, at least in my opinion, is that this distance is controlling the failure mechanism. Now, if you look in the Eurocode 5, when you work with any sort of fasteners and screws and nails, whatever, the Eurocode recommends you to put your screws to a specific distance. There's a limitation, and you can't go too close to your edge. And that's because if your screw is too close to your edge, you have some stress concentration over here that produce a local failure, that produce a splitting of the timber. Now, in my mind, these tabs do not work too differently from a screw, from a fastener. And the fact that they are relatively close to the edge somehow introduce, make this part of the beam subjected to stress concentration and prone to splitting. So when you combine the two essentially elements together, if you work with a 200 section and you further reduce this length over here, you're not just reducing by a factor of 4. Sorry, it wouldn't be a factor of 4 because actually 200 is not really half of the 250. But because this length is actually getting smaller, this is sort of anticipating the failure that you might have otherwise. So shrinking down sections in WikiL Skylark is still a little bit, it's actually difficult to do. And when you shrink down a section, you might experience a different failure mode that you wouldn't do otherwise on the original specimen. Now, this introduced actually a quite interesting challenge for us, because when looking in literature, but this is my personal opinion, and I will be very happy to actually hear other ideas, we haven't found yet a good mathematical model to actually calculate this effect, this sort of close to edge effect that anticipate your failure mode. So the next step in our research is actually a project that we are keep working on in partnership with the Imperial College in London, is to carry out some finite element modeling. They really try to go into the micro details of this distance and try to figure out what is going on in terms of stress concentration, how we can essentially optimize that detail, and if there's a way to increase the capacity by playing with other geometrical properties of the beam. Finally, as a last remark, last hopefully interesting point of the study is about stiffness and about calculating the deflection of a beam. When you work in structural engineering, the typical equations that we use are called Euler-Bernoulli equations, which is a differential equations that essentially, if you know the material and if you know the loads and the static scheme of your beam, in this case simply supported, that you can calculate the deflection based on some algebra and some math. In this case, essentially, we tweaked a little bit the equations, introducing two rotational springs. And essentially, these two rotational springs represent the behavior of the castellated joint. So the fact that we have a castellated joint on the side of the beam introduces a nonlinearity in the problem, or better, a discontinuity in the linear behavior of the problem. So by using digital image correlation, we were able to measure the stiffness of the joint. And by knowing the stiffness of the joint, the elastic stiffness of the joint, we can plug in that into classical equations and we can calculate the deflection of the beam. So there are details here in the paper, but essentially what you can see when we are plotting the calculated deflection versus the measured one, we are quite in a decent agreement, especially for the short span specimens. It's important to know that when you use these equations to design, you normally are looking at the first 1 and 2. So you tend to work, when you're interested in stiffness, you're normally interested in force values that are far from the capacity, that they are in what we call serviceability limit state, and tend to be in the range between 20 and 40% of the maximum beam capacity. And it seems that actually we are doing a decent job over there. Obviously, the more we're getting closer to capacity, for example, here, the latest curve is at 90% of the capacity, we are overshooting a little bit. That's because when you start going to force values near the capacity, you have more linearity in the behavior kicking in. And since our math is linear and our experimental behavior is non-linear, then we start having some mismatches. But I hope that there are results for other specimens. We do a decent job even with 200 series, and with the 250 series, actually we are overshooting a little bit. So it seems that the beams are actually a little bit stiffer than the theory will suggest. This is not bad if we are using these equations for design purposes, because it means we are conservative. But from a research point of view, obviously, we would like to be spot on. And perhaps this is also a topic that we should investigate further with finite element modeling and see if we can adjust these equations to provide even a better accuracy of them. So in this graph, you can see a summary of the experimental campaigns of both OSB and plywood. So the blue points are the current tests that we carried out at Imperial College. So you notice you have 3 specimens for 3 dot points for the 150 series. Notice that we are talking about the bending capacity. So that means we removed the influence of the span, so we can compare the results with each other. We have 3 specimens for the 200 series for OSB and 3 specimens for the 250 series, still OSB. The red triangles are actually the experimental results on plywood that we tested in 2021. And the dashed line is the average, so we can compare to have a better understanding. Unfortunately, at that time, we only carried out a test on the 250 series, so we can't carry out the comparison on the 200 and 150. So actually, the difference between the 250, speaking about the 250 series, between OSB and plywood is actually not too bad. You can see here OSB is around 17 kilonewton meters, whereas plywood is around 19, maybe a little bit more. So if you think about that, that's between 10 and 15 percent difference. So that's actually quite interesting, because what you would have expected if this was a traditional beam, where you essentially everything depends on the bending capacity. If OSB has a bending capacity that is half than plywood, then you would expect at structural level that your rectangular beam would have half of the capacity. But because the Wickel system is more complex because of all how these panels interact with each other, even if you have a material that which structural performance in terms of bending, tension and compression is lower, the fact that it's probably stronger in shear makes up a difference in the way the panels interact to each other at system level. So it's quite interesting that the capacity of OSB beams is actually good, and it's not that far off from plywood. So what does that mean in terms of design? So now this graph might be a little bit more complex, but hopefully will make sense to you if we go through it together. So now imagine that the dashed lines, so we're talking about the capacity over here, the average capacity, they become a cross. So the average capacity in terms of plywood for the 250 series is here. The average capacity for OSB 250 is here. For the 200 series is here. And the 150 is here. Now, the capacity of the beams depends on the section depth. But the question is, how far can we span with each section depth? And what is interesting to know is that you need to know the demand for a specific span. So this is exactly what I plot and what these dashed black lines represent. If you have an L span, which is about 6 meters, you're going to have a moment demand above 16 kilonewton meter. If you have a shorter span, an M span, you have a moment demand that is around 13 kilonewton meter. And the smaller the span, the smaller your bending demand is. Now, when comparing demand for a given span and capacity, you can actually argue which section you should use for a specific span. Now, the way I calculated this black lines is based on Eurocode file. I had to make some assumptions about safety coefficients, some assumption about people's load and people's weight and vertical load distribution, which if you work with a structural engineer should do for you. And that's the process they normally do to verify a structure. So these black lines might change a little bit depending on who's going to calculate them and what assumption they are going to rely on. But essentially what is interesting to me is that if you want to cover an L specimen, an L distance for a floor, then you won't be able to reach it with a 200 series. That's because your demand of more than 16 kilonewton meter is bigger than the capacity, which is around 8 point something kilonewton meter, with safety coefficient and all the stuff all combined together. So if you wanna take an L span, then you need a 250 series, but you can cover the N span with both plywood and OSB. The fact that plywood is more far away from the black line means that you have the capacity is you have more redundancy, you have more capacity spared. No, redundancy is not the right word. You have more capacity spared with respect to the demand, but you're still meeting code regulation. And it means also you can meet the code with also OSB. Now, if you have a span that is an XS span, which I believe is 3 meters, if I'm correct, or 3 point something, then at that point you have the option. You can certainly cover it with a 250 series. You've seen that the capacity is well above the horizontal line, but you can even choose to cover it with a Skylark 200 series. So your Skylark 200 series can meet this span requirements. So the capacity is bigger than the demand. And if you have a XXS span, we are talking about here a floor, so where people walk on and where you may have furniture, you could potentially even using a smaller depth section. What we actually have in the Wikihausa library is slightly different in the sense of the 200 series can cover, I believe, from XS up to L, so that's spot on. The 200 series can cover up to S, so we actually give the opportunity to people to even cover an S span with a 200 series. The disclaimer here is that your structural engineer might have a different, might make some different loading assumptions, or might work with different degree of conservatism. So this black line can move up and down a little bit, and also your capacity beam, which has some safety coefficient sign, can move up and down a little bit. So there's sort of a little gray area between the S demand and the capacity with the 200 series, where if you're, for example, you use a different static scheme. For example, your beam is sitting on 3 supports rather than a clear net span, the demand is going to drop down, the capacity is going to stay the same, so you can potentially cover that. So the message here is that there might be situations in which a floor beam can actually, of the 200 series, can actually cover an S span. It's not unreasonable, but that depends on the actual project by project scenario. So I hope that was clear, but otherwise feel free to let me know. I know this is a difficult graph to explain. I hope that was useful to you. We talked about OSB as a material and its comparison with plywood in terms of mechanical properties. We talked about how these mechanical properties propagate into the wiki-house system. So specifically how wiki-house beams made of OSB compare with wiki-house beams made of plywood. And we even went through quite into detail actually about the testing outcomes. So we talked about failure mechanism. We talked about how these change when swapping one material to the other. And then we talked about also a little bit of the uncertainty that we're still having in providing an accurate mathematical modeling to capturing some of these failure modes. I hope that was of interest to you. If you have any questions, ideas, or you would like to share something, please feel free to comment on the video. I'm sure part of this work can be done better. So we're always here to listen and improve. And yeah, we really hope to keep improving while we test the system and while we deploy it. So thank you very much, and till the next video.